Okay, so we're going to talk about vectors and parametric equations and why they are in the same section. Because they seem like disparate topics. But they're really very much related, and if you're taking physics, you've probably talked about vectors, but maybe not specifically parametric equations. Even though you've done parametric equations in physics, they were probably just never called parametric equations, or you didn't realize that you were doing parametric equations. So let's start with vectors, and I'm just going to do a very, very brief recap of vectors. So let's say I had this vector, -2, 3. So I just want to recap, a couple of things, that this vector's been written in component form, and I'm using the angled brackets instead of parentheses that I would with a point. So let me just kind of refresh us on the words. This is component form. And if I'm calling this vector v, I put a little arrow above v to indicate that v is a vector, not just a point or a scalar or a numerical quantity. So some of the jargon here is that a vector is a quantity with magnitude and direction. So the magnitude of vector v, represented as just the absolute value of the vector, does not just mean that I turn the components positive. It means that I find the length of the vector. So the magnitude is the length of the vector. The length of the vector. So, spelling vector wrong here. Change that. Great. So, usually a picture is really going to help here. So if I drew a picture, the vector -2, 3, that means I can start at any point I want in the plane, and it would be equivalent to, from the starting point, moving left 2 units and up 3 units, putting down the ending point, and then connecting the starting points and the ending points, and having an arrow to indicate the direction in which I'm moving. Now, the most convenient starting point, I think, is the origin. So I usually have my vectors start at the origin. So starting point's the origin. Stopping point is at -2, 3. And the vector's going to have an arrow that indicates that I'm moving from the origin, ending at the points -2, 3. So the vector is that line segment pointed in that exact direction. So the length here, I could just do some Pythagorean theorem, is just the square root of x squared plus y squared. So in this case, that's the square root of -2 squared plus 3 squared, which would be the square root of 13 units. I don't know why I just wrote 19. So the length is root 13, which is about 3.606 units. So that's the length of the vector. The direction of the vector, is, well, it's just the direction that the vector is pointed in. But if I wanted to measure that, I'm usually going to use standard position. So if you notice in the book, there's a bunch of things that you could do, like bearing, and I could say that this is a certain number of degrees north of west and all of that sort of business. But usually I'm just going to use theta, and it's going to be implied that I'm measuring the direction in standard position. The angle in standard position. This is the angle in standard position. I'll usually call that theta. So in this case, I got to be a little bit careful here when I compute this. I can use an inverse trig function. Usually I'll use the inverse tangent function because with the components I'm given the x and the y value. So the direction here is going to be the tan inverse of 3/2. But now I got to be a little bit careful here in the sense that the tan inverse of 3/2 gives me the acute reference angle in standard position. So that's going to give me the angle that's bound between the vector and the x-axis in quadrant 2. But I want to be careful here because if I'm measuring the angle in standard position, I know that it's going to be more than 90 and less than 180. So I'm going to do 180 minus the tan inverse of 3/2, which gives me about 123.7 degrees. So notice I did not do the tan inverse of negative 3/2 here. I just ignored that there was a negative sign there. I thought of this as if the vector was in quadrant 1. I know the tan inverse function will give me an answer between 0 and 90. And then I adjusted that reference angle based on what quadrant I was in. So the picture's telling me I got to do 180 minus the tan inverse of 3/2, because the tan inverse of 3/2 gives me that acute reference angle. But standard position, I want that angle right there. Great, so that's kind of all of the stuff we know about vectors. So let's look at some of the things that we don't know about. Like, I can add vectors together. So I've got this vector v already set up here. It's negative 2, 3. Let's say I had vector w, and let's say vector w was 3, 4. So I can add vectors together. I could do vector v plus vector w. And vector addition's really easy. You just add the components. It'd be the vector 1, 7. Done deal. You want to add vectors, just add the components. It's literally that easy. Now, unfortunately, we don't have the multiplication operation existing between vectors. In other words, there's no way to multiply 2 vectors and get another vector back. But there is an operation that's kind of like multiplication that was invented, and it's called the dot product. So I could do v dot w. So this is the dot product. So the dot product is kind of a way that I can take 2 vectors and quote-unquote multiply them, but the answer is going to be a number. It's not going to be another vector. And then the answer is going to be related to the geometric picture that I would get if I draw both the vectors together. So it's definitely clear here. I want to make some sort of note that the dot product is a number, not a vector. It's really easy to compute. You just multiply the x value, the x components, then you add that to multiplying the y components together. So in this case, it would be negative 2 times 3 is negative 6, plus 3 times 4, which is 12. That would mean that v dot w is 6. So notice it's not a vector, it's the number 6. So the question is why did we make this dot product operation? Like, why did we define this to be multiplying the x components and then multiplying the y components and then adding those results together? Like, why is that a thing that we need a formula for? So it's related to the geometry of the vectors in the following way. So here's my picture. So let's look at the geometry here. So I've got the vector v, which is negative 2, 3. So there's v. And then my vector w is 3, 4. So there's w up there. So the dot product relates basically the angle between the vectors. So if I wanted to find this angle right here, I'll call it beta. If I wanted to find that angle, the dot product is actually related to that angle. So first let's find the angle without the dot product. So if I wanted to find beta here, I should write down what v and w are again really quick here. So it looks like if I wanted to find beta, like what that angle is, looks like beta is going to be equal to 180 minus the tan inverse of 3/2 minus the tan inverse of 4/3. So the tan inverse of 4/3 gives me that acute reference angle. The tan inverse of 3/2 gives me that acute reference angle. And if I do 180 minus each of those, then I'm going to be left with the angle between the vectors, the acute angle between the vectors, which is angle beta. Now, this is equivalent to this relationship. The cosine of beta also happens to equal the dot product of V and W divided by the product of the magnitudes of V and W. So if I've already done V dot W. V dot W is 6. And I've already figured out the magnitude of V, that's root 13. And I've already figured out the magnitude of W. Well, no, actually I haven't. But the magnitude of W will just be 5. Because 3 squared plus 4 squared, the square root of that is 5. And it doesn't look like this is going to give me equivalent forms of beta, but it does. This works. And so right now this seems a little bit mystical, why this would be true. There's kind of nothing, I've offered no explanation as to why this is true or why this is a fact. But this is an example of something that I'm going to throw into the box along with some of the other facts that I've not proved yet this year. So I'm thinking of things like the cosine of A plus B being cosine of A, cosine of B, plus sine of A, sine of B, like those angle addition formulas. I didn't prove those last chapter. I'm not going to prove that the angle between two vectors, that the cosine of that angle is the dot product of the vectors divided by the product of the magnitudes. I'm just not going to prove that right now. Both of these statements are actually statements involving complex numbers. So when we get to complex numbers, they become totally obvious, but right now it's not really obvious at all. So you just have to kind of believe me for now, and we'll use the formula a couple of times, we'll do some problems, and when we get to complex numbers, we'll be able to do the proof very quickly, easily, efficiently, and it actually, it totally makes sense as well. So great, so this is all stuff with vectors. So how does this, or what does this have to do with parametric equations? Okay, so first, what is a parametric equation? So a parametric equation is just where you take any relationship between x and y and you write x as a function of t and y as a function of t. And usually t stands for time in almost every problem. Usually t is time. So you've probably done this in physics, but just never referenced this as being a parametric equation. So the idea that I'm thinking of that people have probably seen in physics before is the idea of like throwing something up in the air and thinking about how does its height change over time, but also how does the horizontal distance from some fixed point that we call the origin, how does that change over time? So let's take a simple scenario here, and I think this was a problem that people were working on yesterday on one of the worksheets, but maybe didn't know how to do. But I think the problem was this. I think it was you're hitting a golf ball, and you hit the golf ball with an initial velocity of 180 feet per second at an 18-degree angle off the ground. And we have to assume that we're hitting the ball straight so that it's not hooking or slicing. It's going straight. And we'll ignore things like wind resistance and things like that. So we'll just think of the only force acting on the ball as gravity, so to speak. So let's... That problem involves vectors. It also involves parametric equations. So how does it involve vectors? It involves vectors because we're given information about the initial velocity of the golf ball. So I can draw, I've got this vector that describes the initial velocity of the ball. So the 180 feet per second that the ball was hit at, That is the magnitude of the velocity vector of the ball. The 18 degrees, the 18-degree angle with the ground, that's the direction at which the ball was hit. Now I can use just basic, simple right triangle trigonometry to solve for the initial velocity of the ball in the x direction and the initial velocity of the ball in the y direction. So it looks like there I could write the equation, the sine of 18 degrees equals v sub y over 180, and the cosine of 18 degrees equals v sub x over 180. I should be saying v sub y sub o, but the initial velocities in each direction. So I can find the components of that velocity vector. So my velocity, my initial velocity vector has the following components. It's going to be 180 cosine of 18 degrees, comma 180 sine of 18 degrees. And if I write that and just kind of round this off, this is going to be 180 cosine of 18 is about 171.191 feet per second. And 180 sine of 18 is going to be 55.623 feet per second. So that is the component form of the velocity. That's the initial velocity in the x direction and the initial velocity in the y direction. And if I put those together, that's the initial velocity vector of the golf ball. So now where do parametric equations come into play? Well, now I can think of two things happening here. And unfortunately, I'm making hand gestures here, which you can't see on the video. But if a golf ball is hit, it's going to be going out, but it's also going to be rising and then falling and hitting the ground. So it's going to go out in the horizontal direction, not affected by any force because I'm ignoring wind resistance and friction, any sort of friction in the horizontal direction. And then it's not going to rise forever because gravity is acting on the ball and it's eventually going to fall again. So I can write two separate equations, one equation for the motion of the ball in the x direction and another equation for the motion of the ball in the y direction, and this would be a parametric equation. So my equation for x is just going to be the initial velocity in the x direction times time. That's it. That describes the horizontal motion of the ball. So x equals 180 cosine of 18 times t. So that equation is saying the ball is going to just continue to go horizontally forever because I'm ignoring friction and things like this. I mean, clearly in real life that's not the case. If I hit a golf ball, it's not going to go like forever.
It'll go really far.
It'll probably go like 10 feet if I was hitting the golf ball. So now the equation for y is going to be slightly more complicated because I need to take into account that gravity is affecting the ball. So now this equation is going to be, if you're in physics right now, you've probably done a lab or 2 or 5 on this. And so this is going to be very familiar. If you're not in physics, you're taking chem or AP bio or something like that, then this is just something, again, you got to take this on faith for now, and you will investigate this fully when you eventually take physics. But the equation is going to be negative 1/2 at squared plus v y sub 0 t plus y sub 0. So let me parse through this equation. Acceleration is acceleration due to gravity. I'm in feet per second here, so it'll be 32 feet per second. In physics, you may or may not see that 1/2 is being written as negative 1/2. I wrote it as negative 1/2 because I'm always assuming that up vertically is positive, the way I define my coordinate system. So I'll just call the acceleration due to gravity 32 feet per second, throw the negative out there. That also works. So if you wanted to, if you're more comfortable with this, I could get rid of that negative and then just making sure that I'm calling A negative 32 feet per second per second. So now I can write my equation for the motion of the ball in the y direction. So it'd be 1/2 times negative 32 is negative 16 t squared plus 180 sine of 18t plus y sub 0, which is the height of the golf ball from whatever I'm calling sort of the origin, like the height off the ground. But I'm defining where the golf ball is resting on the ground at the beginning of the problem to be the origin. So y sub 0 is 0. So I have one equation that governs the motion of the ball horizontally and another equation which governs the height of the ball vertically. So each x and y is a function of time. That is a parametric equation. So you could have been doing this in physics for a long time where you have multiple equations, each is a function of time, just never calling them parametric equations. But that is what is going on here.